Hi Suchitra, I hope I'm audible.
Yes, ma'am.
Okay, we'll wait for a few minutes to let everyone join and then we'll start the session.
Okay.
I hope everybody can see my screen. Can someone confirm?
Yes, ma'am, it is visible. Good evening, ma'am.
Yeah, only the screen is visible or the presentation screen is also visible.
No, no, there is no such presentation, ma'am.
Okay, is it visible now?
Yes, ma'am, visible.
Yeah, yes, yes, it's visible now.
Okay, okay, thank you. Okay, everyone, so welcome to the fifth TA session for Drug Delivery Principles and Engineering. And as usual, today also we'll discuss few topics that were discussed in the last week and few assignment questions based on that. So, in the last week, protein adsorption and tissue engineering are the two major topics that were covered. Protein adsorption is basically the initial and one of the most critical events when any foreign material, such as implant or different kinds of drug delivery devices, are introduced into the body, or when they are in contact with biological fluids. The protein interaction with these surfaces basically determine the subsequent cellular responses and the overall biocompatibility of these foreign materials that we basically design. Either it could be either an implant or other drug delivery devices. And it basically talks about the adsorption versus absorption of these proteins, how they are how they form different layers over the implants, and the adsorption kinetics and models, whether multi-layer or monolayer, whether hard proteins or soft proteins. Different quantification techniques was also discussed, and then basically its application in drug delivery, and how we can enhance or reduce this protein adsorption based on our applications. Next was tissue engineering. Tissue engineering is basically uh, it applies both principles of biology and engineering to restore or replace tissue functions, relying heavily on biomaterials and their interactions and regenerative strategies. So, based on these topics, let's see what all assignment questions we have. I hope everybody can still see my screen. Can someone
Yes, ma'am.
confirm?
Yes, ma'am. Yes, ma'am. You can see.
So this is the first question. Which of the following cells do you think should be commonly used in a recellularized scaffold for skin tissue regeneration? You have to select two correct options here. Please let me know what you think the correct answers are, and then we'll discuss.
Ma'am, it's T cell.
T cells. Okay. One more option.
Mm,
So you have to select two correct options. One and six. Okay, let's see. Any other answer? Anybody else would like to answer?
No, ma'am. No.
Okay, no problem. We'll discuss. Okay, so here the question is asking which of the following cells do you think should be commonly used in a recellularized scaffold for skin tissue regeneration? Now, when you are using a scaffold for skin tissue regeneration, you need to see what all cells are there in your skin tissue that you are trying to regenerate. So, they are mostly keratinocytes, fibroblasts, melanocytes, these kind of cells, right? So the first, fourth options, that is fibroblasts and keratinocytes, the seventh option, these would be the correct answer. Apart from that, T cells, B cells, macrophages, neutrophils, these are all immune cells. Though immune cells are also part of the skin tissue, if you incorporate immune cells into your scaffold, it will initiate further or a very strong it will trigger a very strong immune and inflammatory response, right? Because your scaffold is like an external or a foreign material when you are planning the skin tissue regeneration. So you want fibroblasts and keratinocytes, and then they will start proliferating there, recellularize, recellularize the things, and then it will initiate further interactions, and then it will get embedded in your skin. So the correct answer will be fibroblasts and keratinocytes. Okay, moving on to the end, hepatocytes is basically liver cells, so it's not necessarily needed in your skin tissue, so that is also excluded. Okay, moving on to the next question. Proteins denature on biomaterial surfaces. What factors play an important role in this process? You have to select two correct options here. The options are biomaterial surface chemistry and wettability, biomaterial core properties, atmospheric pressure, amount of dissolved helium in the solvent, the amount of nitrogen in the atmosphere, the partial pressure of oxygen in surrounding atmosphere, or protein stability. What factors displayed here play an important role in the process of protein denaturation? You have to select two correct options here. biomaterial surface chemistry and wettability, biomaterial core properties, atmospheric pressure, amount of dissolved helium in the solvent, the amount of nitrogen in the atmosphere, partial pressure of oxygen in surrounding atmosphere, or protein stability. Which of these two options do you think are correct? Anybody answered? 1 and 7, 1 and 4. Okay. Anybody else would like to answer? Which of these two options do you think play important role in protein denaturation on biomaterial surface? Okay, the correct answer here would be 1 and 7, biomaterial surface chemistry and wettability, and the seventh option, that is protein stability. So the proteins denature on surfaces due to the interactions which are strongly influenced by the surface chemistry and wettability. Based on whether the surface is hydrophobic or hydrophilic, it will change the adherence of the protein. If it is more hydrophobic, it will attract or promote more protein unfolding. That is, the hydrophobic core of the protein will be exposed to this hydrophobic material, and there will be hydrophobic interaction between the two, making a conformational change of these proteins or denaturation at the interface. If it is more hydrophilic, it repels or reduces the adhesion of these proteins. Similarly, protein stability, based on charge, pH, and other factors that are involved, they can uh, they can affect the stability of the protein. If uh, the native conformation of the protein is disturbed by these factors, then it will get denatured on the biomaterial surfaces. So protein stability and biomaterial surface chemistry and wettability will be the two factors that are very important on this on based on the protein denaturation on biomaterial surfaces. Okay, moving on to the next question. Pre-adsorbing of cell adhesive proteins such as dash and des increases attachment of cells to the biomaterial surface, you have to select two correct options here. Options are albumin, fibronectin, collagen, immunoglobulin, transferrin, globulin, IgG, or VEGF receptors. Anybody would like to answer which of these cell adhesive proteins increases cell attachments to the biomaterial surfaces? 2 and 3 and 2 and 6. Okay. Anybody else would like to answer? Okay, the correct answer is option 2 and 3, which is fibronectin and collagen. The pre-adsorbing of cell adhesive proteins like fibronectin and collagen increases attachment of cells to the biomaterial surfaces. So if you have a biomaterial surface where you want to increase more cell adherence, then you can coat them using these proteins, that is fibronectin and collagen. These are key extracellular matrix proteins that is majorly secreted by cells, and they have multiple cell adhesion sites, integrin based binding sites, etc., for cell attachment, and that helps as an anchorage point to cells and helps in cell attachment and proliferation. So coating or pre-adsorbing your these kind of cell adhesive proteins onto your biomaterial surface will help in increasing the attachment of cells. Okay, moving on to the next question. Which of the following is an example of tissue engineering? You have to select two correct options here. 1. Generating whole or part tissue in vitro and replacing damaged tissues in patients. Growing cells on a plastic surface. Adding support or filler material to support the function of damaged tissue. Culturing larvae for silk. Collecting spider silk from webs. Integrating scaffold in cancer tissue so that it allows higher proliferation of cells. Culturing primary cells ex vivo, or culturing immortalized cells. Yes, anybody? Option 1 and 3. Okay. Yes, both of you are correct. Option 1, that is generating whole or part of tissue in vitro and replacing the damaged tissues in patients, as well as adding support or filler material to support the function of the damaged tissue, are two examples of tissue engineering. Okay, moving on to the next question. Adsorption can be which of these two correct options? 1. Bulk phenomenon. 2. Temporary surface phenomenon. 3. Permanent surface phenomenon. Or 4. Driven majorly by gravitational forces. option 1 and 2. Option 2, you have to select two correct options here. Okay, the correct answer is temporary surface phenomenon or permanent surface phenomenon. It based on how long it is staying, or the exchange of the proteins, for example protein adsorption. Based on that, it could be either a temporary surface phenomenon or a permanent surface phenomenon. Okay, moving on to the next question. What is not a strategy to reduce protein adsorption on biomaterials? You have to select two correct options here. Use hydrophilic polymers, coat with PEG, pre-adsorb with albumin, increase roughness, or impart positive charge. Okay, anybody answering this question? What is not a strategy to reduce protein adsorption? You have to select two correct options here. Option 4 and 5. Okay. Okay, option 4 and 5 is the correct answer. Option 4 increase roughness and option 5 impart positive surface charge. So here the question is, what is not a strategy to reduce protein absorption, or basically which of these is a strategy to increase protein absorption on biomaterials? So among these, if you see, increasing the surface roughness increases protein absorption, as well as increasing positive charge attracts more protein, because most of the proteins have slightly negative charge. So increasing roughness and imparting positive surface charge helps in increasing the protein absorption, whereas using hydrophilic polymers, coating with PEG, or using albumin reduces the protein absorption on biomaterials. So the correct option will be option 4 and 5. Okay, now moving on to the next question. The phenomena of displacement of kinetically favored proteins by thermodynamically favored proteins to absorb on a surface is called which of these options? That is Roman effect, Langmuir model, kinetic model, Roman effect, 3D model, or protein absorption model. Which of these phenomena describes the which of these options describe the phenomena of displacement of kinetically favored proteins by thermodynamically favored proteins to adsorb on a surface? Option 4. Okay. Anybody else? You have to select one correct option here. It is a direct question. Which of these phenomena which of these describes the phenomena of displacement of kinetically favored proteins by thermodynamically favored proteins? Okay, option 4 or the Vroman effect is the correct answer. So when your surface or a biomaterial is exposed to these proteins, the initial interaction is based on kinetics, and then whether they are stable thermodynamically there or not, more and more proteins that are there, they replace the thermodynamically stable proteins opposed to the previously attached kinetically favored proteins. So this displacement is called Vroman effect. Okay, moving on to the next question. For transplantation in humans, allografting is one of the most common approach. What are the major drawbacks of this approach? Which of these two options are the major drawbacks of allografting? Option 1 and 2. Okay. Anybody else? Anybody? Option 1 and 2. Yes. Both of you are correct. Lack of donors and spread of disease. These are the major drawbacks when using allografting technique. Okay, moving on to the next question. Which surface is more favorable for protein adsorption and why? You have to select two correct options here. One, hydrophilic surface because it is more charged. Two, hydrophobic surface because it is energetically more favorable to displace water and replace with protein. Three, smooth surface because of available surface area. Or four, rough surface because of available surface area. 4. Okay. What about others? Which of these options do you think is, or which of these surfaces do you think is more favorable for protein adsorption and why? You have to select two correct options here. Okay, the correct answer here would be option 2, hydrophobic surface, because it is energetically more favorable to displace water and replace with protein. And option 4, that is rough surface, because of available surface area. I guess the other answer is not coming here, might be an error, but yeah, option 2 and option 4 will be the correct answer. Hydrophobic surface enhances, because it is energetically more favorable, it helps in displacement of water and replaces with protein. Whether hydrophilic surface does not allow the proteins, or basically the proteins, the outer layers of the proteins mostly interact with this hydrophilic surface, and the hydrophobic core remains stable, which is why it does not get adhered to it. It just interacts and leaves from there. There is not a strong interaction there. Similarly, with rough surface area, there is more available surface. With rough surface, there is more available surface area for protein interaction, which is why it is more favorable for protein adsorption. So option 2 and option 4 will be the correct answer here. Okay, that was all the questions I had for today. If you have any other questions or doubts, we can discuss. Otherwise, we can close this session here. If you want me to go through any other questions again, also let me know. Yes, you can unmute yourself and speak. Shabazz. Or you can type out your questions. I've already finished the session today. I guess you guys joined late, so I'll just go through the questions again. Feel free to stop me, or if you have any doubts or any questions. Okay, this was. I hope you guys can see my screen. Okay, this was the first question that we discussed. Which of the following cells do you think should be commonly used in a recellularized scaffold for skin tissue regeneration? There were two correct options here. So, fibroblasts and keratinocytes will be the correct answer here. Other cells are immune cells or hepatocytes, which are liver cells, which are not very useful for skin tissue recellularization. So, fibroblasts and keratinocytes will be the correct answer here. The next question was proteins denature on biomaterial surfaces. Which of these factors play an important role in this process? So, option 1, biomaterial surface chemistry and wettability, and option 7, protein stability, will be the correct answer here. These two factors play an important role on protein denaturation on biomaterial surfaces. Next question was pre-adsorbing of cell adhesive proteins such as dash and dash increases attachment of cells to the biomaterial surface. Here also there were two correct options. So, fibronectin and collagen, these are two cell adhesive proteins. They have several cell attachment integrin based receptors and other cell attachment points for uh, cell attachment points, which helps in increasing the attachment of cells on the biomaterial surfaces if they are coated with these proteins. Next question was which of the following is an example of tissue engineering? You have to select two correct options here. Generate the correct answers were option 1 and 3, that is generating whole or part tissue in vitro and replacing the damaged tissues in patients, or adding support or filler material to support the function of the damaged tissue. So these two were the correct options. The next question was adsorption. Adsorption can be option 2 and 3, both a temporary and a surface phenomenon. The next question was what is not a strategy to reduce protein adsorption on biomaterials? Not a strategy to reduce, or basically a strategy to increase protein adsorption. Here the correct answer will be option 4 and option 5, increased roughness or imparting positive surface charge. Both of these induces more protein adsorption, so they are not a strategy to reduce protein adsorption. So option 4 and 5 will be the correct answer. This was the next question. The phenomena of displacement of kinetically favored proteins by thermodynamically favored proteins to adsorb on a surface is called. The correct answer here would be option 4, Vroman effect. This is the next question. For transplantation in humans, allografting is one of the most common approach. What are the major drawbacks of this approach? You have to select two correct options here. So the correct answer here were lack of donors and spread of disease. These two are the major drawbacks in allografting approach. This was the next and the last question, that is which surface is more favorable for protein adsorption and why? You have to select two correct options here. So option 2 and 4 would be the correct answer, that is hydrophobic surface, because it is energetically more favorable to displace water and replace with protein. and option 4, that is rough surface because of available surface area. So these two options will be the correct answer. That was all the questions that we discussed today.